The topic we are going to discuss today is related to impossible differential cryptanalysis of reduced round TweAES. And my name is Chao Niu from Shandong University, China. First, we will introduce the motivation and contribution of this work. Next, we will have a brief description of impossible differential cryptanalysis. Then we introduce some properties of TweAES and our key recovery attack on it on the TweAES. TweAES is the underlying primitives of associated data encryption and with associated data scheme estate, which was accepted as one of second-round candidates in the NIST lightweight cryptography standardization project. Multitude TweAES is a tweakable variant of AES 128, and it is identical to AES 128, except it just injects a tweak value every 2 rounds. Next, the motivation and contribution of this work. As we all know, AES is a well-analyzed cipher, which means we have strong confidence in its security. The best attack against the AES 128 in the single key setting only reaches 7 out of 10 rounds. Moreover, compared to AES 128, the TweAES just add a 4-bit tweak. So we're interested in the security of TweAES compared to AES 128 by exploiting the property of TweAES, mainly the influence brought by the 4-bit tweak. We found a mistake of the impossible differential attack in design document, and the it-round key recovery in the design document is invalid because the type complexity exceeds exhaustive search. Motivated by this, we proposed a new 8-round key recovery attack with valid complexity using a 5.5 round distinguisher. Next, we introduce impossible cryptanalysis. The original impossible differential attack is a variant of differential attack proposed by Knudsen and Beham. Impossible differential analysis is different from classical differential cryptanalysis, which uses high probability differences to recover the key. On the contrary, it uses the difference with a probability of 0. Its basic idea is to exclude the candidate keys that lead to the difference with the probability of 0, because the ciphertext encrypted with the correct key cannot have such a difference. And to find this impossible differential, we usually use the miss in the middle approach. We denote the difference on the ciphertext on the plaintext X alpha, and the difference on the ciphertext C beta. Then the probability of this differential alpha propagated to beta is 0. In practice, we deduce the difference alpha propagated through the block cipher in the forward direction, and the difference beta propagated in the backward direction, and the difference beta and alpha meet together. When the difference propagated to the middle and the contradiction occurs, we call this alpha and beta an impossible differential. Then we will introduce a 3.5 round impossible differential of AES. The gray block denote active block difference. The white block denote the active zero difference. The input difference alpha is kept active through the S-box operation, and after shift row mixed column propagate to this state. And similarly, we derive the propagation of the output difference beta in the backward direction. We can get this state. Then the contradiction occurs because of the branch number of AES mixed column operation is 5. We can say the active byte in input state and the output state of this two column is 4. So the contradiction occurs. Note that all the operations except for the add tick are identical to that of AES 128, including the key schedule. We introduce the add tick operation of TweAES. The 4-bit tick is first expanded to 8-bit using a linear code, and then the 8-bit value is exclusive OR into the state at an interval of every 2 rounds. Define T0 to T3 as a 4-bit tick, and the internal variable T exclusive OR is equal to the exclusive OR of the 4-bit tick T0 to T3. Then T4 to T7 is generated by the exclusive OR of the internal variable and T0 to T3. Then we have the 8-bit expanded tick T0 to T7. Then we will introduce the first property of the add tick operation. We find the linear expand code can lead to 2 kinds of tick difference. When the number of the active bits of the 4-bit tick is odd, in this case is 1, 0, 1, 1. Then the generated 4-bit tick is the inverse of the original 4-bit tick, as shown in the picture is 0, 1, 0, 0. Then, when the number of the active bit is even, the generated 4-bit is the same as 4-bit tick. In this case is 1, 0, 0, 1. And the generated 4-bit tick is 1, 0, 0, 1. This can make sure that the tick difference can propagate to at least 3 columns. In this case, the tick difference added to the state, then propagate to 1 round AES. Then the active state is W2, which have 3 columns. This means the tick difference can cause a good diffusion. The second property is the different involved k bit in attack. In the design document, they use the strategy to lengthen the distinguisher by using the tick difference to cancel the state difference at the beginning and the end of the distinguisher. So, as shown in picture, the beginning and the end of the 6th round distinguisher is equal to the tick difference. We can say when the tick difference is 1001, after expand is 1001, 1001. Then the 8-bit expanded tick is exclusive all into the state after one round inverse AES in the key recovery attack. We can say the involved key is the main diagonal and the diagonal below the main diagonal of the state. And at the end of the distinguisher, the difference on X9 is equal to the difference on the expanded tick. And after one AES round, the involved key is the 0, 3, 6, and 7 byte of the state. Next, when the tick difference is 1100, we can say after one inverse AES round in the key recovery attack, the involved key, K1, is the main diagonal and the diagonal below upper. The main diagonal and the diagonal upper the main diagonal. And in the back direction, we can see the involved key is the 0, 1, 4, and 7 byte of K9. We tried all these 4-bit tick differences, and a total of 15 kinds of tick differences. And then we can determine that one cannot use a different tick difference in a key recovery attack because of the different involved key bits. Then, motivated to make a valid key recovery attack, we try to find a distinguisher that cancels the state difference with tick difference at the beginning, but remain one active byte at the end. Before introducing our 8-round key recovery attack, we will give a proposition of AES S-box. When given one pair of input and output difference, delta in and delta out of AES S-box, we can get a pair of input and output values, which means there exists one solution y on average for which the equation sy exclusive sy exclusive delta in equals to delta out. As we can see, half of the entries in the difference distribution table of AES S-box are 0, and half are non-zero entries. The non-zero entries have two solutions. So, with a pair of input and output difference, delta in and delta out, we can get a 0 solution or two solutions, which means on average one solution of y. Next, it is the differential of our 8-round attack. We can see the end of our 5.55 round distinguisher has only one active byte on Z7. In this attack, we use 4 distinguishers with the same tick difference, where these 4 distinguishers have one active byte at 0, 4, 8, and 12 byte of Z7. In this case, after the mixed column operation, the active state of the W7 is the first column, which means these 4 distinguishers have the same involved K9 in the K recovery attack. First, we collect the data under one pair of tweak, which the tweak difference is 1, 1, 0, 0. And then, after the encryption of all these plaintext pairs, we can get ciphertext pairs. And we save the ciphertext pairs by checking the difference at the white block is 0 difference. So we can get n plus 48 power of 2 remaining pairs finally. That is has the difference on the plain text is this form, and the ciphertext text pairs difference at this form. And then we can get, and then for all this n plus 48 power of 2 remaining pairs, we can get x2, the difference on x2, because it's equal to delta p. As mentioned above, the 8-bit expanded tweak is exclusive or into the least significant bit of each byte in the first 2 rows, due to the difference on W2 is fixed difference. That is equal to the tweak difference. Then we can deduce the difference on the state Y2, because the inverse operation of a mixed column and shift row is linear operation. Now we have the difference on X2 and the difference on Y2, which are the input and output difference of the S box. So with the proposition 1, we can get X2, the value of X2. Then we can get K1 by exclusive or Y2, the value of Y2 and the value of P. Next, we can see the number of possible differences on W7 is 10th power of 2, because of the active byte of Z7 is just 1. But we have 4 distinguishers, so it's the possible difference on W7 is S power of 2 plus times 4, which is equal to 10th power of 2. So for these differences, we can compute the difference on X8. Similarly, we can get the difference on Y8 from delta C. Then use proposition 1, we can also get the value of Y8. Then use Y8, we can get 10th power of 2 different K9. After this procedure, we can use one pair valid ciphertext pairs to save 10th power of 2 different sub-key, K1 and K9. Then, we can get the mask key by exhaustively search the candidate keys and the remaining key bits of K1. And using the key schedule, we can compute the mask key. Thank you for watching.